Welcome back to TalkTensors. We know you want to get straight to the core of important research, especially in ML and AI, without getting lost in the weeds. Today, we're doing a deep dive into a really fascinating paper. It's called Why the Brain Cannot Be a Digital Computer: History, Dependence, and the Computational Limits of Consciousness.
Yeah, this one definitely caught our eye. It questions a really foundational idea.
Right. The whole computational theory of mind that the brain is basically a biological computer. This paper uses information theory to argue, well, that maybe it just doesn't compute, literally.
Yeah, exactly. It's an idea that's been, hugely influential for decades, especially in AI. The brain is hardware, consciousness is software, that kind of analogy. But this paper presents a quantitative challenge. It says, look, if you actually calculate the information needed for conscious experience, especially how it depends on the past,
it just doesn't fit.
It seems like it might not fit within the classical digital framework. The numbers get huge.
Okay, so for listeners trying to grasp the limits and potential of AI, this is pretty relevant. The paper argues that the information needed for just one conscious moment, compounded by its history, might actually exceed the brain's physical storage capacity, at least as a classical computer.
That's the core claim. They try to quantify it. How many bits would you need to represent every distinguishable conscious state across a lifespan?
And they bring in this idea of historical dependency.
Right. That's crucial. They start by defining a stimulus frame.
Okay, what's that?
It's like the smallest unit of conscious awareness you can distinguish across all senses: vision, hearing, smell, taste, touch.
Kind of like a pixel, but for consciousness?
Sort of, but much richer. It's integrated. They draw on psychophysics, information compression ideas, like JPEGs or MP3s, to estimate the bit count for one frame.
And it's not just raw data, right? You said it's richer.
Exactly. It's the quality of the experience. So they go through visual acuity, auditory discrimination, the sheer number of smells we can supposedly tell apart.
That Bush did study, right? The trillion odors.
Yeah, that one. And taste, touch, spatial detail, texture, temperature.
So they add all that up.
They sum it all up, trying to be conservative, and land on about 200,000 bits.
Wow. 200,000 bits for just one conscious snapshot.
For one integrated frame, yeah. Even before you get to the history part, it's already a lot of information.
Okay, so now the history part. This is where, for me, it gets really interesting, especially thinking about AI models.
This is the core argument. Our experience now isn't just about the sensory input now. It's deeply tied to what came before.
They have that wine tasting example.
Right. Perfect illustration. You're drinking red wine, experience is smooth, you switch from white to red.
Even if the red tastes the same chemically.
Your conscious experience is totally different. Surprise, maybe confusion. The phenomenology changes because of the immediate past.
So the same sensory input, different conscious state, purely because of history.
Exactly. They argue this isn't just memory influencing interpretation. It's fundamental to the structure of consciousness itself. It's historically embedded.
And it's not just linear, like A affects B affects C.
No, it's more complex. They describe it as recursive nested. T1 depends on T0. T3 depends on T2, which itself depends on T1 and T0. And crucially, the relationship between these moments, these blocks of experience, adds another layer. Higher order dependencies.
Okay, so the informational requirement isn't just adding up the frames.
It scales much faster. They show it mathematically. If L is the bits for one frame, the state at time step n doesn't just need L bits or even n times L bits added independently. It needs something closer to n multiplied by L bits because of all the integrated historical context.
So CTN, GSTN is STN1, ST0, needing NX L bits. That's very different from the simple CT1 needing just L bits.
Precisely. The traditional computational view often implies the latter, a state based mostly on current input. This model suggests a vastly greater information load due to this deep temporal integration.
Okay, so we have this potentially enormous snowballing information requirement. The big question then is, can the brain actually handle that physically?
That's the next step. They look at the neuroanatomy. How many neurons? How many connections, synapses? How much information can each synapse plausibly hold?
And they use current estimates for this.
Yeah, and they lean towards generous sort of upper bound estimates for capacity, around 86 to 100 billion neurons.
Okay.
Average of maybe 7,000 synapses per neuron.
Right.
And then drawing on studies, maybe 4 to 5 bits of information storage per synapse, like different strength levels or states.
So you multiply all that out.
And you get a theoretical upper limit for the brain's classical information capacity. Using the synaptic model, it's around 2.8 quadrillion bits.
2.8 quadrillion. Okay.
They also mention a simpler binary neuron model, which gives much less, like 86 billion bits. But let's stick with the larger synaptic number.
All right, 2.8 quadrillion bits capacity. Now, how much did the consciousness model require?
This is the punchline. They calculate the requirement for, say, a 100-year lifespan, assuming maybe 15 distinguishable conscious frames per second, which seems plausible, maybe even low.
And the total comes out to?
Around 9.46 quadrillion bits.
Whoa. Okay. 9.46 quadrillion required versus maybe 2.8 quadrillion estimated capacity.
Exactly. There's a significant gap. The requirement is over 3 times larger than the estimated classical capacity, even using generous assumptions for the brain's hardware.
So the paper's conclusion is basically the numbers don't add up if the brain is just a classical digital computer storing this conscious history.
That's the main thrust. The information load implied by temporally integrated consciousness seems to exceed the brain's classical bit capacity. It suggests something else might be going on.
Something beyond standard computation.
Or maybe our estimates of capacity are wildly off, or consciousness isn't quite as information-rich as they model, but the discrepancy is large enough to warrant serious attention.
It definitely challenges the status quo. Now, thinking historically, especially for our listeners interested in AI's roots, the brain as computer idea has been dominant for a long time.
Oh, absolutely. Since the mid-20th century, cognitive science, AI, it was fueled by this analogy. Information processing, mental states as computational states, think Turing, Newell, Simon.
Symbolic AI, then connectionism, now deep learning. They all kind of inherit that computational framework.
They do, to varying degrees. Of course, there have always been critics, philosophers worrying about qualia, subjective feel, meaning, things that don't easily map to computation.
Like Searle's Chinese room argument.
Exactly, or Chalmers' hard problem. But this paper comes at it from a different angle, a quantitative information theoretic limit. It's a novel critique.
So it adds a new dimension to that ongoing debate. Okay, let's pivot to our novel notions segment. If this paper is right, or even partly right, that classical computation isn't the full story for the brain, what does that open up? What are the implications for future research, maybe even for building AI?
Well, it pushes us to think outside the standard digital box. If the brain can't store this information classically, how does it achieve consciousness? This leads to some pretty speculative but exciting ideas. One major avenue is exploring non-classical information processing in neurons.
Meaning, beyond just bits and logic gates.
Exactly. Could the brain be using physics we don't normally associate with computation? Maybe something at the subneuronal level, quantum effects even?
Quantum mechanics in the brain, that sounds pretty out there.
It is speculative, definitely.
Yeah.
But people are looking into it. The field of quantum biology is growing. They're finding quantum effects in photosynthesis, bird navigation. So the question becomes, could things like quantum superposition or entanglement, which give quantum computers their power, play any role in the brain's information handling, especially if classical capacity seems insufficient for consciousness?
How would that even work in a warm, wet brain? Isn't quantum stuff usually super fragile?
That's the huge challenge, maintaining coherence. But perhaps there are biological mechanisms we haven't discovered. Maybe certain molecular structures or the cytoskeleton within neurons could shield or utilize quantum phenomena for brief critical computations.
What kind of evidence might point towards that, even indirectly?
Well, perhaps some aspects of brain structure or function that look inefficient or redundant from a purely classical viewpoint might actually be essential for enabling these non-classical processes. It's a long shot, maybe.
But the paper gives a reason to look.
It provides a potential need for something beyond classical. If the information requirements are truly that vast, we have to consider alternatives. Finding such mechanisms would obviously be revolutionary, not just for neuroscience, but maybe for computing too.
A completely different kind of AI substrate, potentially.
Potentially. Again, highly speculative, food for thought. But this paper definitely cracks open the door to considering such possibilities more seriously.
Fascinating stuff. So wrapping up this deep dive, the core takeaway seems to be this significant challenge to the brain as digital computer model based on the immense information load of historically dependent consciousness.
Right. It suggests the sheer richness and temporal integration of our experience might require more bits than our neural hardware, viewed classically, can offer.
Which definitely gives us, and you listening, a new lens for thinking about the mind-body problem, the nature of consciousness, and maybe the fundamental hurdles in creating truly conscious AI.
Absolutely. It forces us to question some basic assumptions. If you want to dig into the details yourself, check out the link to the paper in the description. It's a dense read, but thought-provoking.
Definitely. Thanks for exploring this with us on TalkTensors. As a final thought to ponder, could this apparent informational limit not just be a biological constraint, but maybe a fundamental property of what consciousness is? Something to chew on. Until next time.